Let's take a look at some carboxylic acids here. So these are organic molecules that contain two things. They've got an OH and they have a double bonded oxygen, and that's bonded to a carbon. So another way to say that is that they have both the hydroxyl group, that thing, and they have a carbonyl group, which is kind of that thing, plus a carbon, and they combine to make this COOH functional group, or it's just at the end of the molecule. So here is that carbonyl group in general, and you add that to the hydroxyl group in general, and you end up with the carboxyl group in general. So there you go. So again, this is at the end of your chain. That's at the end of your chain right there. So carboxylics have the following general formula. Again, this H here stands for any old number of carbons. This is considered to be like our primary carbon, though, and that will be part of our longest chain length. That'll come into play when we name. So here are a few simple ones. This one only has one, methanoic acid or formic acid. Here we've got two, and here we have the benzene ring attached to the carbonyl functional group. So let's look at naming next. So we're going to name some acids, and we'll only look at ones that contain one of these COOH groups. So first thing is you're going to select the longest chain that involves the carboxyl group, and like I mentioned before, that this C here is going to end up being the primary C1. So you're going to name the parent chain by dropping the E from the corresponding alkane name and changing it to oic acid, like we saw in the other ones, methanoic acid, and kind of so on. If necessary, indicate the identity and location of the substituents on the parent chain in front of the carboxyl acids names. So let's take a look at a few examples here. So let's name the following. So we identify this group here at the end. So this is in fact a carboxylic acid, and then we go ahead and we count our carbons here. We've got 1, 2, 3, 4. So 4 is bute, so this one instead of butane should be butanoic acid. There's our oic acid part. What else? So this one is fairly similar. You can still see the carbonyl functional group, and we have 4 carbons, 1, 2, 3, 4. So again, we're dealing with the butanoic acid. This time we have a couple of bromine groups, and they are on the 3rd carbon. So 3,3 dibromo butanoic acid. And one more here. Again, we'll identify our longest chain. Don't be tricked, it's just 3 long. So again, there is our carbonyl group. So we've got some kind of propanoic acid here. And then we've got a methyl group, and this would be off the 2nd carbon. So 2-methyl propanoic acid. So here's a few common names. Building up, you can see we've got methanoic, ethanoic, propanoic, butanoic, pentanoic, hexanoic. So if you could remember those names, that'll be an advantage. There's the general formulas. Frogs are polite, being very courteous could help you remember that. So with that group there, we've got a couple of dipoles on the go here, and so it ends up being a highly polar molecule, and this is going to cause us to have some high boiling points. So there's that same graph. You can see we've got acids up top. Those are representing the highest ones. Alkanes are representing the lowest, and again, it has to do with polarity and molecules having attractive forces for each other. So this leads to high melting points and boiling points, this polarity. It also causes these acids to be very soluble, up to 4 carbons. And you can see that. Let me fix my bracket. There we go. So you can see that we have a high degree of solubility up here, and then it just falls off the edge here. That's just the way of the molecule, the way of chemistry. So preparing some carboxylic acids. So we're going to have a 2-step process. We're going to start with an alcohol, primary alcohol, and we're going to change it to an aldehyde. And then we're going to take that aldehyde and change it to the carboxylic acid. And so in general here, we've got our primary. It undergoes an oxidation reaction. That's what the O stands for. It makes the aldehyde. So we're creating this portion here. And then once again, we're doing the oxidation reaction, and then this oxygen sort of gets added in, if you will. So there's kind of a rule here with these reactions. It says that an oxidation reaction, which is this stuff here, the O, what it's trying to do is it's trying to increase the number of bonds that carbon shares with oxygen, while at the same time decreasing the number of bonds it shares with hydrogen. And we might be able to see that a little bit better here as we go through the full example. So step one, we'll take our primary alcohol, and I've just left it open-ended here. I haven't said exactly which alcohol it is. And we're going to do the oxidation. So what's going to happen here in this step is we're going to take these two hydrogens, they're going to be removed, and they're going to kind of join onto that thing to create water. And what we're left with is a double bond has been created. So like I said earlier, in the oxidation reactions, we're increasing the number of bonds between carbon and oxygen. We've increased it. It used to be 1 here, and now it's up to 2 right here. So we've increased it. And I guess technically we've also decreased the number of hydrogens. That bond is gone, and it has now appeared over here. So the oxidation has, the rule has come through. So in step 2, let's rewrite this molecule here. We'll bring that down. And once again, we're going to do the oxidation. And then once again, we need to realize that we're going to increase the number of oxygen bonds while decreasing the number of hydrogen. And so what that's going to do is it's going to take this oxygen and kind of stick it in between the carbon and the hydrogen, if you will. So in a sense, what we're doing is we're decreasing the number of hydrogen bonds because this hydrogen will no longer be bonded to the carbon. So it's decreasing the number of carbon-hydrogen bonds, while at the same time, we're increasing the number of carbon-oxygen bonds because now this oxygen is going to be bonded to that carbon. And there we go. And well, it doesn't look pretty, but you can see we have our carboxylic group there. Now we're going to look at the close cousin of the carboxylic acid. This is an ester, not an ether, but an ester. So our structure is that it's really like we've got a carboxylic acid and we are replacing the hydroxide group with an alkyl group. So here it is. So here's our carboxylic acid. So this is the derivative part here. And for us to change to an ester, notice that we've still got this part intact. It's just the H is gone and it's been replaced by some kind of carbon chain. That's where the alkyl oxyl group is referring to. So naming esters, the first thing you want to identify is the long chain that contains the OH group. And this is going to act as our parent chain. So spot that first. Name the parent chain by dropping the E. So if it's propane, you drop the E, it becomes propanate, propoate. Now the other part of the chain, this is going to be adjacent to the single bonded oxygen. That's just going to be a carbon chain. So we're just going to name that carbon chain like any kind of carbon chain that you would name. So let's take a look at a few examples. So here's your first one. So again, our first thing says you want to spot the longest chain containing this thing here. Okay, so there is our longest chain. It's got 1, 2, 3, 4, 5 carbons, so penta, so pentanoate. Then we're going to look at the stuff over here, which is only 2 long. That's an ethyl group, so we have an ethyl pentanoate. Here's another one again. So even though the right side of this chain is longer, we're still interested in this being our parent chain because it's connected to the CO group. So we have 3 there, so that should be a propanoate. And then counting this up, 1, 2, 3, 4, that's butyl, butyl propanoate. Now this one drawn in stick form has a substituent group off of it right there, so a subgroup. So first things first is you're still going to say, okay, we got a carbon there, a carbon there, a carbon there, a carbon there, so it's 4. So we're talking about a butanoate. And then what we're going to do is we're going to say, okay, that methyl group looks like it's off the second carbon there, so that would be the second carbon, so we'll call that a 2-methyl butanoate. And then we'll turn our attention to the other side where looks like we have 2 carbons, so that should be an ethyl-2-methyl butanoate. So now we're going to draw the following. We want to do a methyl methanoate. So to do this one, I'm going to start with my oxygen double bonded to my carbon. And since it's an ester, by the O8 ending, I'm going to put an O there. And this one's going to be pretty simple. So it tells me my longest chain connected to the doubly bonded O is a methyl group, or methane. That means I already kind of have it, so I'll just add a hydrogen there. And then this group is going to go onto this side, and it's methyl as well, so it's CH3. And there you go. There's your simplest ester. We can look at perhaps one that might be a little more complicated, an ethyl-3-methyl. Correct this one on the fly here. I should probably have a dash between the words and numbers. So ethyl-3-methyl hexanoate. So we'll draw the hexanoate part first. There we go. So there's our O8 part, and 1, 2, 3, 4, 5, 6 makes it a hex. Now we have a methyl group on the third carbon, so we should number this 1, 2, 3. And notice I left a spot there, no hydrogen. So there goes that group. And then my ethyl group will just go down on that side there. Ta-da! And there is our compound. Esters have pleasant smells, and they're used for different scented things like soaps, perfumes, and cosmetics. And here's a whole bunch. Now, the names are just a little bit different, but you'll recognize them. These are sort of more using the formal names. And the iso. Iso just means you've got 4 carbons, and they're shaped like this. Like they're not in a straight chain. One of them is branched off. That's what an iso group is. And the acetate is also referred. That's again just the common name of that chain length. So raspberry, apple, pineapple, rum, peach, orange, strawberry, honey, wintergreen. There's quite a few there. Properties of esters. So these are polar molecules. Why are they polar? Well, because they've got that. They got a dipole here. Yeah, you got a couple dipoles probably on the go there. That should be negative. So yeah, you got a couple of dipoles. So it's a polar molecule. But what they lack is they lack that OH group, right? That OH group that would have been right there. Had I drawn this nicely, you would have seen it. Well, it would have made a carboxyl acid if I changed that into an OH. So it's not there. So no hydrogen bonding. So how does that affect things? Well, it causes our esters to have lower boiling points and melting points than the carboxylic acid cousin. Maybe not necessarily every other thing, just compared to the carboxylic there. And since they're polar, they will be soluble in water very slightly. So 2 reactions here, and they're kind of opposites of each other, so pay attention. We've got the esterification. And so what this means, esterification, is we take our carboxylic acid and an alcohol, and we're going to combine them to make the ester. So you can take any carboxylic acid you want. So there's one, and this is just the general form. And again, it's the acid because it has that OH there, kind of ironic. And we're going to add that to our alcohol. It doesn't say what kind of alcohol. It's just a primary alcohol, but it doesn't give the chain length. Now, what's going to happen is, for us to create the carboxylic acid, we need to get rid of this hydrogen. And what it's going to do is it's going to switch places with this R. So the R is going to attach to the chain, ta-da, and HOH leaves us with water. So esterification makes an ester and water. Now the opposite is a hydrolysis of an ester known as saponification, and this is a process where soap is actually created, although it's not this example, but the breaking of a covalent bond by a molecule by the addition of the elements of water, which splits the ester into the acid and the alcohol. So it's just the reverse. So here is one. Again, it's named with the acetate molecule, so it's not necessarily, again, the convention we have followed. It's a sort of different one, so we can name this differently. But anyway, so there is your there's your ester, and we're going to react it with water. So that H and OH is going to play a part. So what we're going to do is, again, remembering this is HOH. So simply what's going to happen is this stuff right here, I guess, is going to exit, and it's going to switch with the hydrogen. And you're going to attach the OH in its place. So there you go. So the OH, that OH is gone onto that carbon there. Ta-da. And you can see that our chain has now just added an H in the end. So that H has gone onto that molecule, and it's just kind of flipped around too.